All right, let's start with let's start with a little bit of review type of stuff here, and then we'll get into tomorrow. We can do a little bit with the worksheet. We can talk more about the worksheet and the calculator stuff here in a little bit, or tomorrow. So let's take a look at a few things. These are some notes. These weren't specific notes we took the other day. Just some stuff I've got from previous years. Let's see. That's number 21. We did that one last time. Let's see. Number 20 was our homework today, right? Wasn't that one of them? Okay. Here was number 21 where we did negative root 2 and root 2. And then, so this was kind of the new stuff, and then I didn't talk about this, so I do want to add that into there. Okay, so last time we were doing kind of these limit problems with the table. Okay, we don't really care what happens right here. On this line as x approaches 3, but if we can see that these are, now I did change that. Now, the way I've got it written here, if these were negative and these were positive, what would you say the limit was on this one? If you saw a table like this, what are you going to say? Does not exist, right? Because from the left of 3, we're getting these y values at negative 5.37, and to the right, they're positive, and so they're not coming in and approaching. The cars are not meeting, and so that would be does not exist. If these were positive here, then obviously there's our limit, 5.371. Okay, so that's kind of what you were doing on that worksheet with doing the table, but we'll talk more about that. We'll talk more about that tomorrow. Okay, and then we also had, well, I need to find the right page of notes here. Hold on a second. I thought it was that day, but that must have been this one. Here we go. That's what I was looking for. Okay, so this is what we had up here on Friday. So we were talking about, again, we'll go over this in a lot more detail tomorrow as our review. So I just want to briefly, being Monday, kind of catch up with where we're at. We're talking about doing the derivative, the definition of the derivative. Very important we understand that. The definition of the derivative is this limit right here. And so working that out gives us the derivative at a certain point, or derivative for x. And then we learned our power rule, which is another way of doing a derivative, so we can talk about that and be able to do that. And then we spent a bunch of time doing these limit problems, okay, with the various ways of doing those. And then we came back and now focused more on derivatives. And I do want to kind of give an analogy today, because I did talk with a couple people who were having some confusion about limit, derivative, and when you do what and whatever, and it really is important you understand what's happening. And so I've tried to come up with an analogy of what that would be like from an algebra standpoint, see if it helps you to organize your thoughts on some of this. But so anyway, we got back into derivatives and doing stuff with the chart, and local max, increasing, decreasing, number line type problems, which we're going to work a few because you had some of that in your homework. So we already did number 19, that was earlier. Okay, here was a limit problem, like we do, and how does that relate? And then if we go back, then the new stuff that we learned on Friday, which was this definition of the continuous function. A function's continuous if it meets these 3 things. That is, if the function is defined at point A, so these 2 situations would certainly fail that. The function is undefined if there's a hole or there's a vertical asymptote. So it would not be continuous. Remember, continuous means nice and smooth, no breaks or holes or anything like that.
Not for you, though.
We're all going to get out of here. Here.
No, you won't.
I will.
Okay, you can.
Sam sits right there. He's gone.
Sam's going, but Alex is
And
here.
Alex,
Alex is here. He went.
he just.
Awesome. Thank you.
All right. So, so a function's continuous if it meets all 3 of these. If it fails any one, it's not continuous. So function's got to be defined. If it fails, it would look like one of these situations. The limit must exist, means the cars must meet. Well, here's 2 situations where the cars don't meet. So again, the function's not continuous. And then the limit has to equal the output. Here would be a situation that would fail that. The limit exists because the cars would meet here, and the function is defined because there is an output there. But unfortunately, those two aren't the same. So this is not continuous either. Anything that's weird is not continuous. If the graph, if you never lift your pencil, right, it's nice and smooth and so forth, then a function is continuous. It's going to be a pretty strange situation. Now, a lot of these you'd be able to tell pretty easily. Like, for example, would be piecewise. If you have a piecewise, there's a good chance it might not be continuous. And that's what problem 66 and 67 were about. We're going to talk about those. And then also if you get some vertical asymptotes, like you get zeros in the bottom, zeros in the denominator, that kind of thing, then the function's not going to be continuous. All right, let's start with this today. So that's just kind of a quick overview of what's going on. All right, let's start with this. I tried to make an analogy about, with a couple of different people, trying to make an analogy about limits and derivatives, and like your worksheet today was about limits, but it was also about derivatives. I mean, and what is the connection there? What is the difference? What's going on? Okay? Well, first of all, a derivative is what? It's the slope, right? At one point. It's the slope of a tangent line of a curve. Now, it's also rate of change, right? But that is slope. They're the same thing. Those are interchangeable terms. Slope, rate of change of a function. That's what a derivative is. So on the one hand, we have a problem that says f of x, equals, I don't know, something, let's just make something up, x squared, and we want to find f prime of 4, right? One way. Now there are other ways, and we'll do this tomorrow, this will be part of our review tomorrow, but one way of doing f prime of 4 is by using the definition of the derivative. What's the definition of the derivative? The formal definition of the derivative. The limit definition of the derivative, sometimes called. What is it? Limit as h approaches 0. In this case would be f of, if we were doing this, would be f of 4 plus h, but you're right, it's f of x plus h, but if we're wanting to do f prime of 4, right, minus f of 4 all over h. Now, to go from here, what would we do? We would work out this limit problem, right? Now, how are the different ways we have of working out a limit problem? What's one way we can do this? What's that? So one way would be to go ahead and take 4 plus h and plug it into here. So we get 4 plus h squared minus f of 4, which would be 16, right, all over h, right? And then FOIL it out, right? Do algebra, get the answer. This would be probably in a no calculator situation. That's probably the type where you would see that, right? But what if the direction said use a calculator table? What would you do with this? You would graph what? This part, right? That's what you did on today's worksheet, right? You took the blue part, you graphed it, except instead of an H, you put a X, and you worked it out, you saw where it was, and you, at that point, you were doing a limit problem, but it was inside of doing a derivative problem. Does that make sense? And then since we realized that doing a derivative problem, one way of doing a derivative problem was to use the definition of the derivative, which involves a limit, and then we had to solve that limit. So at some point I said, oh, you know what, we should practice doing some limit problems. So we did a whole page of stuff like this. Limit as x approaches 3 of x squared minus 9 over x minus 3. Now, does that have anything to do with a derivative? No, that's just a limit problem, right? Now we could do some algebra to that. Or we did another page where we could do you know, we did some calculator ones, right? Or we did some graph limits. You know, I just gave you a picture like this and said, you know, what's the limit? You know, as x approaches 2 or whatever. Oh, it does not exist, right? That kind of. So you've got this. So the overarching thing we're talking about is derivatives, slope, rate of change, whatever. It turns out in the process of doing these that we need to be able to work out a limit sometimes. So we better know how to do limits. So we spent some time doing some limit problems. So on the quiz, you'll have some limit problems. And I just don't want people to get confused when you're doing these limit problems thinking about slope or derivative, because it doesn't have anything to do with that, right? Here's a derivative problem that might have a limit in it, and if you have to, you work out a limit. And then we spent some time practicing limits. Now here's my analogy. To me, this would be like this in algebra class. I happen to be doing this in my Algebra 1B class right now. We're working out a problem like this. Actually, we haven't gotten to this yet, but let's say you had a problem like this, and the directions were to solve. What would you do? Actually, you guys are having to do this right now, aren't you, on some of your derivative problems? But anyway, so the directions are to solve. What do? Subtract 6, right? Get 0 on one side. And then what? Factor, right? And it'd be what? Minus 6 plus 1. And so x would equal, and we would be done. Now, so here's my analogy. So my analogy is we're in calculus all about right now derivatives. And what does that mean and how do we find them and that kind of stuff. One way of doing derivatives, the long way of doing derivatives, is the definition of the derivative. The definition of the derivative is this. So in working this out, we have a couple ways to do it. So we have to work out this limit, maybe with a calculator, maybe with algebra, right? So since we have to do that in these derivative problems sometimes, we practice just doing limits for a while because that's part of this. In algebra class, we want to solve these equations and we want to find out what x is. In the process of doing that, we have to do what? We have to know how to FOIL. So guess what we do? We spend some time practicing how to factor. Now, do you see how these are different questions? Right? You see how this is a whole different question than this? But they're kind of connected, they're kind of related, right? Here we factor this, we just go in here, we do this, we go x and maybe plus 8 and minus 5, right? Something like that. And we just do a bunch of factoring problems just to practice, because inside of this problem, we need to have that skill. Does that make sense? So that's kind of what's happening here with this idea of limit and derivative and how it all fits together. So I don't know. Maybe that's helpful. Maybe that just made it worse. I don't know. But it's really important you understand the overall picture of what's happening here. All right. So let's take a look at homework. Maybe start with number 66. So number 66 says you've got this function, right? What is it? Ax plus 1, and then x squared. Did I have that right? And that is from when x is less than 2 and x is greater than or equal to 2, correct? And the question says, find the value of a for which x, the limit as x approaches 2 exists. Okay? And if a has that value, does f prime exist? Okay, so what'd you do? What'd you do here? Anybody got an idea? Plug a 2 in for x. What we have here, for the limit to exist, we have a line that goes until 2, and then we have a parabola that takes off from there. I don't know if that's what it looks like, but that's potentially what could happen. Would the limit exist if this happens? No. What would have to happen for the limit to exist? The parabola would have to take off from there. So the way you do that is where it breaks is when x is 2. You plug a 2 in for x, you get 2a plus 1, and you put a 2 in here, 2 squared is 4, and so you solve this, and you get a equals 3/2. That's what a would have to be for the limit to exist, because if a is 3/2, then these two would have the same y value, and we would end up with this right here. Okay? Then the second question. If a is 3/2, does f prime of 2 exist? So let's say this is 3/2. Does f prime at 2 exist? Any ideas of how to calculate that? Plug a 2 into where? If you put a 2 into here, you get 3 plus 1, which is 4. And you put a 2 into here, you get 4. They have the same y value, but we knew that. That's what we did right here. All that means is when this one ends, the other one takes off. Let me show it to you this way. What if the line ends here and the parabola is this part here? This is the part of the parabola we're at. I don't know if that is, but let's say it looked like that. Does a derivative exist right there? Because what is that? Sharp point. The derivative doesn't exist. What would have to happen for the derivative to exist? It'd have to be smooth as it takes off. So when I've talked about continuous, a function's continuous, nice and smooth, it doesn't even have to be smooth, really. It could be a V-graph. That's continuous. You never lift your pencil. Smooth is actually the function's differentiable, which we're going to get to in a minute. I'm going to have you write it down. But the derivative exists everywhere. So there might be a sharp point here. Even though one ends and the other takes off, there could be a sharp point. So how do we tell? Well, we need to know what the slope is on this one right here. And we need to know what the slope is on the parabola. How can we find the slope? Well, yeah, right, because it's a line. So what is the slope of the line? 3/2. How can we get the slope on x squared? The shortcut rule, the power rule. What's the derivative of x squared? 2x. So this one, the slope is 3/2. On the other one, it's 2x, but we're at 2, so the slope is, the derivative is 2x, but at x equals 2, that would equal 4. So is it differentiable? Or does f prime of 2 exist? No. 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 Because these are not the same. The slope on the line is 3/2, but then the slope suddenly changes to 4. If it's going to be smooth, okay, so let's summarize what we just learned. Because this goes to number 67. Did you have to do 67 also? Yeah. Okay. This is what I love about 66 and 67 is they're the exact same questions, but they ask them differently, right? So for the function to be continuous, there can't be a break. So that means the y values have to be the same at 2. For the derivative to exist, the slopes have to be the same at 2, which means you need f prime. So you do the derivative of each one, and the slopes have to be the same at that point. That's what will make it smooth. If the slope is 3/2 when it comes in, and it's 3/2 when it leaves, you're going to get a nice smooth transition. If the slope is not the same from coming in to leaving, you're going to get a sharp change. And that's going to be undefined slope. Slope doesn't exist. So that's how we would answer 66. So now look at 67. 67 says, what is it? Ax squared. Help me out. And what's the other one? 3x minus 5. And that's when x is what? What's it break?
X is less than
2 again? Okay, so less than 2 and then greater than or equal to 2. Again, we don't even care which one it's equal to at 2. That just means where the hole would be filled in. You know, where this be a filled in circle. So it's at 2. So look at the questions in A and B though and compare them to the last part. It says find the value of A. Well, what do you mean find the value of A? Well, it says suppose that the function is continuous at 2. Well, to be continuous, what's that mean? You can't have a break. They have to have the same y value. In other words, the limit has to exist, which is the same question they just asked in the other one. So if this is going to be continuous, we plug a 2 in here, we get 4a plus 3. And we plug a 2 in here, we get 6 minus 5, which is 1. So a has to be negative 1/2. Has to be. Okay? A has to be negative 1/2. You plug a 2 in for x and set them equal to each other. They have to have the same y value to be continuous, because otherwise you'd have a break. Okay? All right, so now we know a is negative 1/2. Now, it says, is the function differentiable at 2? Differentiable means the derivative exists. So it's the same question as 66. Just ask a different way. So is it differentiable? So what do? We do the derivative with our power rule. So we bring the 2 down in front. We get negative 1x squared. No, just x. Excuse me. And the other one would be 3. You plug a 2 in. So that'd be negative 2. Here it's 3. So no, they do not have the same slope. So it is not differentiable at 2. This is something we'll get into more, but that was kind of this new thing we learned yesterday. Now, if you want to write that down, or on Friday. Now, I did not have you write this down, so maybe we should do it right here. A differentiable function. Okay, we talked about what continuous means. That's those 3 things. We've got to know those 3 things. Okay? The function has to be defined, the limit has to exist, and the limit has to equal the output to be continuous. That means you never lift your pencil. There's no breaks or holes or anything. But to be differentiable, it's a little higher bar. Not only does it have to be continuous, so it's a little bit of a rectangle and a square thing, right? It has to be continuous. So if you have a square, it has to be a rectangle, and all the sides have to be equal. Well, to be differentiable, it has to be continuous. You never lift your pencil or anything, and the derivative has to exist everywhere. So I put up 2 examples where they would be continuous, but they're not differentiable. The derivative doesn't exist at a sharp point or at a vertical tangent. Okay? So if I told you you had a square, you would know you also had a rectangle. Same thing here. If you have a differentiable function, you know it's continuous. You know not only is the derivative existing everywhere, you know there are no breaks or holes or anything. But if you have a continuous function, it might not be differentiable. If you have a rectangle, it might not be a square. But if you have a square, you know it's a rectangle. It's the same thing. Okay? All differentiable functions are continuous. Not all continuous functions are differentiable. Okay? So those are some terms we often see in the directions, and when we see that, it says assume f is a differentiable function. Well, as soon as you see that, you just know it's nice and smooth, derivative exists everywhere, you know, no sharp points, no breaks, no gaps, nothing like that. All right. I want to look at a couple of problems from this thing right here. Okay? We're starting to get into the point where we're learning enough calculus. We can start looking at thinking about the AP test and what's on the AP test and some of the practice tests we'll be working on as we get ready for our midterms and stuff like that. And so I want to show you right here, and you can write this down, not write down, whatever. I don't care at this point. This is just, I just want to show you a few examples. So here's a multiple choice. This is no calculator, okay? And this is one of our sample kind of practice tests that we work on for practice problems. And so right here, very first problem, right out of the chute, is a limit problem, right? No calculator. Anybody have an idea what we're going to do? Conjugate. Now, first I would say plug in a b, right? B minus b is 0. Square root of b minus square root of b is 0. 0 divided by 0 means keep going. right? You see those radicals, you're thinking conjugate pair. So I'm going to multiply radical x plus radical b, radical x plus radical b. So the point here is kind of, hey, we got to remember this stuff, right? We're going to see this stuff later on, right? We'll be doing this packet maybe in late January. And right off the bat, here will be this problem. So we multiply there, we got b minus x, we got radical x plus radical b. We FOIL that, we got x minus b. Now, can those cancel? Almost. Factor out a -1, then it becomes negative b plus x, which of course is the same as x minus b. Now we can do what? Now we can plug in our b. So we get radical b plus radical b, which is 2 radical b, and then the -1 out in front, and so A is our choice. Notice if you forget the -1, they also have that choice in there, right? I mean, so you got to be careful. All right, there's one right there. And we don't have to go very long before we see another kind of familiar problem with the graphs all piecewise and weird stuff going on. The graph of a function f whose domain is the closed interval 1, 7 is shown above. Which of the following is true? The limit as x approaches 3 is 1. No, the limit is the cars would meet right up here at 3. So that is not true. Limit as x approaches 4 is 3. No, this car's down here, this car's up here, that limit does not exist. The function is continuous at 3. No. Now, this is a good one to talk about. Yesterday, I told you that one of the things that you may have to do on the quiz is I give you a picture like this, and I might ask this right here, is it continuous? And then if no, tell why it's not. So why is this not continuous at 3? And I want you to use the formal language of those 3 things. Which one of those 3 does this violate? The last one, right? The limit is up here. Remember what those 3 are. The function has to have an output. It must be defined. The limit must exist. And then those 2 things have to be equal. So this has an output. The cars meet up here. The limit exists, but they're not the same. So the limit as x approaches 3 does not equal f of 3. That'd be a great answer on a question like that. The limit as x approaches 3 does not equal f of 3. That's why that is not continuous. But for this, all we have to do is eliminate. Is it continuous at 5? Do you have to lift your pencil? No. So it is continuous at 5, and just to double check, does the limit as x approaches 6 equal the output at 6? What's the output at 6? 1, but the limit does not exist because the cars don't meet, right? So D is your choice right there, okay? So look at that. Right off the bat, very beginning of the test, we get this. And then here's the last one I wanted to look at. Yep, so we had a couple of questions that were plain old limit questions, nothing to do with derivatives or anything else. But now we get back to kind of our main theme of what we're interested in this stuff for, and it's about derivatives. So f prime of 2. Okay? Now, how do we find f prime of 2? Forget this function for a minute. So if I ask you to find f prime of 2, we've talked about multiple ways we could do it. What's one way we could find f prime of 2? Definition, the long one. But if it doesn't say, use the definition, then don't do it. Don't do it. It's going to specifically say, use the definition. Okay, so what's another way then? The power rule. Well, unfortunately, right, that doesn't work with absolute value. Okay? What's another way? What's another way we found a derivative? Derivative means what?
Table.
Slope. Well, okay, table. Now you're getting back to limits, I think. That was limits where we did a table. What's another way we did slope?
Graph.
Graph. Right? And sketch tangent lines or that kind of thing. A graph. So here, now this is not going to be, I'm not going to do this to you on the quiz tomorrow, or Wednesday. On the quiz, what I might do is put one where you could do the power rule, right? I might put one where you could do the power rule. We'll practice that tomorrow, okay? We'll deal with that tomorrow. But on this one, we would graph it. Is this not something we could graph? Better, we need to be able to, absolutely. It's a V graph that is up, how many?
Sorry, up 3.
Up 3 and right 2. So it's a V graph that's up 3 and right 2. And then it goes like that. And they want the slope at 2. Right there. That's how we would answer that question, would be a graph. But you got to think of the different ways we have of doing f prime. There's the limit definition, which you'd never want to do unless they tell you to do it. Or if all these answers look weird, like with limits and stuff, then you might go, oh, maybe I have to do that. Or the power rule, right, the different rules we have, which doesn't work with absolute value. But absolute value is an easy thing to graph. So we just graph it, and it would say, oh, that's a sharp point. What if it would have said f prime of 3? Well, you said 1, right, because the slope is 1. Okay. All right, very good, very good. So, let's go back to your homework questions on 52 and 54. Are there any others besides 52 and 54 that somebody wanted to ask about?
33.
33.
It was like find 3 antiderivatives.
33. Find 3 antiderivatives of little g. Good question. So what did they tell you? They said that big G prime is equal to... No. I'm sorry. I wrote that down, didn't I?
Sorry, no, yeah. The
Big G.
big G prime is G.
Yeah, big G prime is little g. That's what they told us, right? And they said that big G is like that. Okay. They want 3 antiderivatives of little g, right? Well, what is the antiderivative? Forget this for a minute, right? What is the antiderivative of little g? Big G. That's what this says right here, right? This says that big G is the antiderivative of little g. Now you're saying, well, no, it says that the derivative of big G, I'm sorry, I said that. This says the derivative of big G is little g, which means that the antiderivative of little g is big G, right? Which we already kind of know. We said that with capital letters, that's what it's going to be. So 3 antiderivatives of big G, well, or little g, what's one? Well, big G. That's one. What's another one? It's really kind of a trick. Plus 1. What's another one? Plus 2. Plus 3. Right? Because what happens if you do the derivative of this? What happens to the plus 1 or the plus 2 or the plus 3? They go away. And remember we talked about that vertical shift thing? When you do an antiderivative, if you go from f prime to f, there's a bunch of different ones that are all just vertical shifts. So all we do is we just do this. Now, normally what happens when we do an antiderivative is we'll just tack on a plus c. Didn't I mention that the other day? Have you ever seen a plus c in your life? Okay, somebody in the other class must have asked that. So if I gave you this, little f equals 3x squared. We did talk about this the other day. What would big F be? Can we just do that one in our head? We did talk about that power rule earlier. It would be x cubed, right? But it also could be x cubed plus 1 or plus 2 or plus 3, right? So a lot of times when we do antiderivatives, not going to be something you have to do on this next quiz. We just stick on a plus c, c for constant. So when we do antiderivatives, a lot of times we will stick on a plus c. Because when we do the derivative to check it, the plus c just goes away. So that's what that question was about. But it's a notation kind of thing. All right. Let's talk about 52 and 54. Let's do 54 first because it's just kind of a, it's very much like number 20. Number 20 was a number line problem, okay, which we can look at again tomorrow. We'll probably do something similar to number 20 again, a number line problem, local max, local min, chart kind of stuff. But 54 is one that asks it about position, a position and a part. This is the first time you're seeing this. And what was this? It was 3t to the fifth
Yeah, minus
plus 60t. Now I just want to explain this briefly. What it says is you have a particle on the x-axis that is moving on the x-axis. What I want you to think of, here's the reason we do these kind of problems. This is a very popular kind of problem. On that sample test, I guarantee I could find about 5 problems that talk about particle moving on the x-axis. Okay? All it is the Bismarck, North Dakota car problem. Remember we talked about being at Bismarck, which is 0, and if you're over here to the right, to east, you're in the positive, and if you're over here on the left, you're in the negative. Well, it's the same thing on the x-axis. Over here, you're in the positive. Over here, you're in the negative, right? If I'm moving to the right, what do we say about that, physics people? What's positive? The velocity is positive, right? Now, it's important that we say that, because what if I'm over here in the negative position, but I'm moving to the right? My velocity is still positive, because think about what my x-axis number is. Now let's pretend instead of Bismarck and a highway, let's pretend there's an x-axis on the floor. I'm over here at -5. And then I'm at -4, and -3, and -2. What's my position doing? It's increasing. It's getting negative and less negative, right? And then I go past 0. Now it's 1, 2, 3, 4, right? It's positive, getting more positive. It's increasing. So what I have is a chart problem here. Okay, what I have is a chart problem. So I want you to think of it this way. I want you to think of, now the function's called x. That's kind of weird, but since the particle's on the x-axis, that's its output. So t is time. So at 1 second he's somewhere, 2 seconds he's somewhere on the x-axis. X is actually the output here, not the input. So think of it as x, x prime, and x double prime. That's like position, velocity, and acceleration. So in our chart. So his position is increasing when his velocity is positive, and it's decreasing when his velocity is negative. So that means it's moving right when his velocity is positive and left when it's negative. So when it says when is he moving to the left, it's really asking when is the derivative negative. That's the key. Once you understand that, then it's just like problem number 20. It's a number line problem. So you simply do the derivative, 15t to the 4th minus 75t squared plus 60. We set that equal to 0. We can factor out a 15. This is possible for the quiz. You might have to do this kind of algebra without a calculator. Okay? This does factor. It looks kind of strange because it's got the t to the 4th, but if you look carefully at it, this would be t squared, t squared. This would be -4, -1. Okay? And then those break down even more. So we get t plus 2, t minus 2, t plus 1, t minus 1. Okay? So that gives you t equals plus or minus 2 and plus or minus 1, but it's said in the problem that t is positive. So we can ignore the negatives. So what we have is a number line. Now I'm going to label that x prime because I'm trying to find when x prime is negative. Anytime, whoops, it's a 1, that's a 2. So 0, 1.5, 3. So this is just like number 20. Anytime we want to find out if a function is positive or negative, we start by finding when it's 0. Because then we can do a number line and check in between, and that's how we find out when it's positive or negative. Okay? And so we take these numbers here and we plug them in. I would suggest right here. To me, that's a good place to plug them into. So I put a 0 into here. That'll be a negative times a negative is positive. Put a 1.5. Now you got to do a little bit in your head here. 1.5 squared is 2 point something. It's less than 4 though, so that's negative. 1.5 squared, take away 1, that'll be positive. And then put a 3 in there, that'll be positive, that'll be positive. So it looks like between 1 and 2 is when this particle is moving to the left. The number line tells us the story. Okay? So what's happening is this particle starts out going to the right, then it stops at 1, it goes back to the left, it stops at 2, and then it goes back to the right. Just like the Bismarck, North Dakota problem, except now we're using an equation to deal with it. But this is the work. I mean, this all would have to be there. That's the only way to do this problem. Okay? You're going to have that kind. It's a local max min problem. This is a local max. This is a local min. Now, in this problem, that means this is when he was farthest to the right, and the other one's when he was farthest to the left. You know, as he was going, kind of a local max, local min. All right. 52. Okay. Yes, we have time. We have time for sure. 52. This is a really tricky problem. A lot of stuff going on for the first time seeing one of these. What's it tell? What's it say? X cubed plus K. All right. So this is really on the tough end of the scale. To me, a problem like 54, now it's the first time you saw one with the particle moving left, so that makes it a little tougher this first time you saw it. But that's a very basic kind of problem, the old number line problem. So number 19, number 21, number 20 that you had to do today, number 54, to me, that's very basic. Do the derivative, set equals 0, get a number line, da-da-da. Max, min, charge stuff. This takes that to another level. You've got to really kind of understand what it is they're talking about and go a few levels and a few steps before you understand what's going on. They're talking about x-intercepts with this. 1, 2, and 3 x-intercepts. I don't know. And this would be no calculator too, by the way. And how in the world would you put a k into your calculator anyway, if you're going to graph it, right? So we got to start thinking about this. What's a k do to this? Shifts it up and down. What's this graph look like? A cubic, right? It's going to go up, could come back down, and then go up again, right? So we got to know all those things. And so then we start thinking about it. We say, oh, okay. If it goes up and does that, it's got one x-intercept. Now, how could it have 2? I like that word, grades. If we shifted this down until that point just touched, so something like that, then we'd have 2. How can we get 3? Move it down just a little more. And then you'd have this. Now what happens if you keep moving it down? Pretty soon this will just graze the x-axis, right? Just touch it. And then you'll only have 2. And then you keep moving it down, then you'll be back to 1. Okay, so now we're starting to see the problem. Now, do you notice how that involves the k, right? It's the vertical shift that's making it happen. So we want to find out what vertical shift will make this happen, and the key points are what? The local maxes and mins. This is a local max-min problem. It didn't seem like it when we read it, but this is a problem about local max and min. How do we find where those are? Do the derivative, set it equal to 0, because the local max and mins are when the derivative is 0. And we know, since this has a leading coefficient, we know it has to have a local max first and then a local min. Remember when I said it'd be good to know what a cubic looks like in some problems? Here's a great example. To know what this cubic would look like and what direction it has to go. Because we know that about cubics, we know it's going to be a local max and a local min. So I'm going to do the derivative. The k disappears, right? What's a derivative of a constant? 0. So that disappears. We're going to set that equal to 0. Well, that's going to be an easy thing to solve. We're going to take out a 3x. We get x minus 2. We get x equals. So which one of those is local max? 0. And that's local min. Now, I could do a number line, right? I don't really have to in this problem because that's not really what it's asking. If this was a local max min problem, I would need to do that. I'd need to put a 0 there, put a 2 there. I'd pick some points here, right? I'd plug them into here. If I put a -1 in there, that's negative. -1 in there, that's negative. Put a 1 in there, that's positive. 1 in there, that's negative. Put a 3 in there, that's positive, that's positive. So this graph goes up, then down, then up. But I knew that already, right? So local max at 0, local min at 2. So whatever. But there it is. Now, what do you do? Okay, that's where the local max and mins are. So I could actually draw my graph of this. I know I'm going to have a local max at the x-axis, and my local min is going to be here at 2. I need to plug them into the original, right? Because what do I want to have happen? I want to know when they land right on the x-axis. That's what I need to know. I need to know when they land right on the x-axis. So I'm going to plug 0 into my function. And I'm going to get 0 minus 0 plus k. I just get k. And I'm going to plug 2 into my function. So 8 minus 12 is -4 plus k. Did I do that right? Is that right? Okay, now. Okay, what good does that do? What did I say I wanted? I wanted to know when these y values were 0. I needed to know right when this min and this max were going to be touching the x-axis, which means their output is 0. So when will this one have an output of 0? Oh, when k is 0. And this one will have an output of 0 when k is 4. Now remember, this one is my minimum, right? So as I'm shifting down, when my minimum just touches is going to be when k is a 4, right? And when my max just touches is when k is a 0. So between 4 and 0, I'm going to have 3. So it wanted to know, what values of k will I have 3 x-intercepts? When k is between 0 and 4. When will I have 2 x-intercepts? When it's exactly 0 or exactly 4. And when will it have 1? Less than 0, not x, k, or greater than 4. So when k is greater than 4, that's when my minimum is just touching. When it's greater than 4, it's going to be shifted up and I'll just have 1. And when k is less than 0, it'll be shifted down so far that it'll only. So that's a really tricky problem. Think of everything you had to go through to be able to get that. But the cool thing about that is to be able to do a problem like that, but to realize that it was about the max and mins. So it gives you a little taste of where we're going down the road after we really figure this out about where's the max and mins, where's the function increasing, where's it decreasing. These are the kind of things we can learn about situations, about what's happening in situations, because the max and min, it was dependent. Solving this problem was dependent on knowing where the max and mins were, what was going on. So we found them, and then we could go from there. All right, probably not going to be anything quite like that on your quiz. We'll stick with more of the basic like 54, number 20, those kind of things. All right. We'll spend some time tomorrow looking at the worksheet if there were any of those you had issues with, but essentially, and then we'll really spend time tomorrow really focusing on probably what I'll do is I'll throw some problems out at you and say, okay, do this, give you some of those, and really kind of go through the review process with the time we have, depending when the lockdown situation is. But then get ready for the quiz. All right. So, but at this point, we've kind of went through the homework, that relates to it and so forth. We'll practice some shortcut type problems and those kind of things. All right. So what we want to do now is go ahead and talk about some stuff. So we're going to switch gears here a little bit. We're going to talk about some stuff that is not on the quiz. All right. Now, you never know. Sometimes seeing what comes next, what comes ahead, helps you a little bit on the quiz. But could, maybe. I doubt it. I don't think it's going to affect it one way or the other. So, all right. So what I want to start here with you is a derivative rules list. I want to get, now we're going to add to this, we'll probably rewrite it. At some point, I'll probably just give you a PDF, send you a PDF or even print for you a list of these rules eventually, once we kind of have. Okay, but I think there's some value in writing down some of this stuff. All right, so the way section 5, 6, and 7 are organized, which is the rest of chapter 2, section 5 is kind of a whole separate thing. And we'll deal with that later in the week. 6 and 7 are really just more rules like the power rule, which is what we're going to start writing down right now. It's the rules for exponential functions, for log functions, for the other trig functions. Okay? And then we can just do chart problems, and we can do all the same kind of problems that we're doing now. So from that standpoint, there's not much new. It's just we're going to learn some more derivative rules. We won't be limited to just the power rule. So let's start by writing down a couple, and I want to use this notation we talked about the other day, Leibniz. Okay, so let's start with the very some of the simple ones we've talked about. And I've never put them kind of in this format, so let's do this right now. So let's say we have a constant times a function. For example, let's say we have a 3 out in front of an x cubed. So when we do the derivative with the power rule, what happens to that 3 out in front? It just stays there, and you bring the exponent down, and you times it, right? Or what if you had 3 sine x? What's the derivative of that? 3 cosine x, right? The 3 just hangs out there and stays there. So the rule is whenever we have a constant in front of a function, it just stays in front of the function, and we do our derivative as normal. It's called the constant multiplication rule. Okay. All right. Another rule we have is that if I have a function plus another function, or minus. So if I have x cubed plus x squared, how do I do that derivative? Do each one separate. So the derivative of f plus g is simply f prime plus or minus g prime. That's what this rule says. Now, it doesn't seem like that big a deal, but it is because it doesn't work for multiply. We talked briefly about that. It doesn't work for multiply. I'm not going to give you any like that, so don't you have to worry about it. Okay, but it works for plus or minus. All right. What did we say about a situation where you've got a constant on the inside? We haven't done one of those for a while. And we'll review that a little more tomorrow again. Remember when we said you have sine 2x? Anybody remember what that derivative is? What you have to do with that 2? Remember when you had to kick it out? We talked about having to kick it out because what it does is it compresses the graph, so it makes all the slopes in half as far, but it also makes them twice as steep. And so what happens is we have to kick out the k, and we leave the k on the inside too. So we do our derivative like normal. So there's the f prime there. The k's still on the inside, but then we have to kick out a k on the outside. So that's something we talked about with derivatives. So really these could be on the quiz, right? And we'll review some that look like this tomorrow. All right. And then we had our power rule. Okay, so the derivative of x raised to the n power is n times x to the n minus 1. So this is our power. So these are just kind of our shortcut derivative rules that we have so far. So we don't have to do the definition, the limit definition, the long one. Okay? Okay. So there's a couple we've been talking about, so let's keep going here. There's a couple we've been talking about that we never formally, have written them down, but we've never written them down, and that's e to the x is its own derivative. Right? The derivative of e to the x is just e to the x. Now remember, if there would be a 2 inside of there with the x, you'd have to kick out a 2, or whatever. But it's not a power rule. We don't bring the x down in front. Power rule's only if you have x raised to a number. X raised to a number. Now, there's another one that goes along with that. What happens if you have a different base? What happens if you have 2 to the x, or 3 to the x, or something else other than e to the x? Now, luckily for us, e to the x is what we see most of the time. Well, here's what it is. It works very much like e to the x does. It's its own derivative. However, there's a multiplier that goes on to it. The natural log of b, whatever the base is. So, for example, the derivative of 2 to the x would equal 2 to the x times ln 2. 2 to the x times ln 2. Because the only difference between 2 to the x and e to the x is it's not quite as steep as e to the x. Okay? And so the slopes aren't quite as much as their y values. E to the x, remember, the cool thing about e to the x is its y values were the same as its slopes. 2 to the x, its y values are not the same as its slopes. So we have to multiply them by this factor. And that's the rule. Just have to memorize it. Okay? Next page. Logs. This is what section 2.6 is about, is exponentials and logs. Let's start with the most common log we deal with, which is natural log. Now, this is an interesting one. Because most derivatives stay within the same family. If you have x to the third, the derivative is 3x squared. You have a power kind of function, your derivative is a power. Derivative of sine is cosine. Your derivative of a trig function, you get another trig function. You do the derivative of e to the x, you get e to the x. You do an exponential, you get another exponential. Logs is the exception. The derivative of ln x is 1 over x. That's it. 1 over x. So what would be the derivative of ln 2x plus 3? It would be 1 over 2x plus 3 times, you got to kick out something. No, the 2. Remember we said anytime you're multiplying on the inside by something, remember back here, anytime we multiply the x by something on the inside, we have to kick that out. So right here, we're multiplying on the inside by a 2. We'll have to kick out a 2. Now I can put that up on top is my answer. So my final answer, I could write 2 over 2x plus 3. That would be the answer. Now, remember, your calculator will do these for you. You can check these on your calculator, okay, as we're practicing. Now, again, these are not going to be on the quiz. I was going to check that one for you just so you can see. Takes a while. All right, now what about other logs? What about logs with other bases? Well, just like with exponentials, it's very similar. It's the same rule, but we have to tack on this multiply. Except it's, instead of tacking on LNB like we did with the other one with exponentials, we tack on 1 over LNB, which is kind of easy to remember because the derivative itself is already 1 over x. So think about this example I gave you. If we would have done this instead of an ln, if we would have done log base 7, let's say, then this would, and it would have had a 2x plus 3 in there, you'd have had 1 over 2x plus 3, then you'd have to kick out a 1 over ln 7 because of the rule, and you'd have to kick out a 2 because of the rule about a constant on the inside. So you can see how it can really start to get tricky with all the various things we throw in there. Okay? And over the course of the next several weeks, we'll be working a lot on these. Okay, so it's, we'll have a lot of practice time on these things. For right now, we want to get these rules written down and start to begin the process of just kind of thinking about them and memory. Okay? Now, just to show you that. So, if I was to do a, come on. Right here, the derivative is right here. If I was going to do that, derivative of x, and do ln 2x plus 3. Yep. Okay, I'm not sure what that yellow. Domain of the result might be larger than the domain of the input. We don't have to worry about that. That's a new one. I remember never seen that come up before. It's something with the updated operating system. Okay. A few more to do here. Section 2.7 is then about the trig function. So we've just dealt with the exponential and log functions and what their derivatives are. And now we've got the trig functions. Now we already know the derivative of sine is cosine. But there's 5 other trig functions. What is the derivative of cosine? Well, it turns out that it is negative sine. Now remember when we did this, we looked at the sine graph, we plotted its slopes, and we saw that it made a cosine. Well, same thing here. If you think about cosine, think about what its slopes do, and you kind of plot it, you would see that it's a negative sine graph. Okay, let's do the derivative of tangent. Tangent. The derivative of tangent x is secant squared x. And again, if you had a 3 in front of it, the 3 would just stay there, so the derivative of 3 tangent x would be 3 secant squared x. If you had a 2 inside that x, you'd have a 2 inside and you'd kick out a 2. So all those other rules we said before still apply. But this is just going to be a memorized situation, okay? Which won't be a problem because we'll use them so much. There'll be a couple that we don't use very often, and so we'll have to make sure we're kind of memorizing those. Okay, so those are the 3 main trig functions, and then we have the 3 reciprocal ones. So let's go through those. So the derivative of secant x is secant x times tangent x. This is one that we'll have to work a little harder to memorize. We don't see it a whole lot. Derivative of secant x is secant x times tangent x. The derivative of cosecant x is closely related. It is negative cosecant x times cotangent x. There's kind of a pattern here with the what are called the co-functions. Do you ever think of, I don't know if Mrs. Payne ever talks about this, but you notice the trig functions, there's a so-called co-function, there's sine and there's cosine, there's secant, there's cosecant, there's tangent, there's cotangent, right? If you look at their co-functions, they're very similar derivatives except with the negative. The co-functions always have a negative on it. So derivative of sine is cosine, derivative of cosine is negative sine. Derivative of tangent is secant squared. Oh, we haven't gotten to that one yet. Derivative of secant is secant times tangent. Derivative of cosecant is negative, and then cosecant, cotangent. And so you might be able to guess then, if the derivative of tangent is secant squared, what would be your guess as the derivative of cotangent? What do you think? Negative, no, cosecant squared. Cosecant squared. So the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. So if you can kind of memorize those, you know, the other ones kind of come easily with the negative in there and so forth. And those are the derivative rules for the trig functions. Now with that, that's a fairly complete list already of derivative rules, because we already know if we add them together, we can just do their derivative separately. We know if we have a number in front, it just stays there. We know if we have a number on the inside, we kick it out. You know, so we already have some of those things that we can combine with these. So we can already be able to do with those rules a fair number of derivatives with those. Okay, so that is basically what there is. We're going to do the quiz Wednesday. I want to get you started on the homework here a little bit. So go ahead and pull out your book, your assignment sheet, and all that stuff. I'm going to give you this assignment. Now, to be honest, this is kind of technically your assignment for Thursday. But you got to think about what's going to happen here. So on Monday, today, I'm going to give you this assignment, which is in 2.6 and 2.7 on your assignment sheet. Okay, it's the line right under where it says solving equation. So this is like 6, 8, 16 through 30 even, 35, and then this one's 10 through 13, 18 through 34 even. So this is really technically for Thursday. We're not really going to go over it till then. Okay, so you can plan your week and how you want to get this stuff accomplished. Okay, tomorrow we're going to review, and I'm not really going to have any review problems. We're going to kind of review in class. I'm going to throw some out to you in class, but there really aren't. There just isn't in the book a good set of just kind of review problems. You have to go back over notes, go back over old homework, that kind of thing. But we'll try to spend some time in class doing a fair number of those kind of things. So there won't really be an assignment for Wednesday other than to get ready for the quiz. And then on Wednesday, obviously we have the quiz, and then after that I've got a solving equations review worksheet that you're going to do. So that's for Thursday. And then also this. So I don't know that you want to save all of that for Wednesday night, I guess is what I'm saying. So you might want to, you know, get this done tonight or be thinking about it and work on it and so forth, so that you're not having to do all that. But we really won't talk about it and go over it till Thursday. There's no sense going over it tomorrow when our focus is for Wednesday's quiz. Okay? So that's kind of where we're at. So let's take a look at how this starts out. So let's look at number 6. In section 2.6. Okay, so number 6, this is on page 138. Page 138. It says use theorem 12. Now, all that is, whenever they talk about theorems in these homework, they're just talking about these rules. Okay, so it'd be this rule right here. So in your book, when they wrote out the rules, when you go back and look, they called them theorems. Okay, you know, don't worry about that. So right here, this is the rule we'd be talking about right here. Log base 10. Right? So there's our rule. So they want us to find, what do they want us to find? H prime of 1/10, H prime of 1, H prime of 10, and H prime of 100. Well, how are we going to find them? This is something you're going to hear me say a lot this year. Now, as we get ready for our quiz on Wednesday, we've already talked about how can I find H prime of 10? Well, the long way, the definition, blah, blah, blah. But that's not what we're using. We're talking about the shortcuts, right? That's what these derivative rules are, the shortcuts. So what you'll hear me say a lot is if you want to find H prime of 10, the first thing you do is find H prime of x, right? If you find H prime of x, then what do? Plug a 10 in. That's all you got to do. So what we need is H prime of x. So that's what our rule is, right? So H prime of x is the rule, right? That's it. So what's the rule say? So the derivative of this would be what? 1 over x times 1 over natural log of 10. 10, right? Isn't that what the rule said? Right here? It's 1 over x times 1 over ln of the base. The base is 10. So there's our derivative. That's h prime of x. So what's h prime of 1/10? 1 over 1/10, what's that? 10 times 1 over ln 10. So that'd be 10 over ln 10, right? Which is just a number. That's just leave it though. Some decimal, you could type it in and get it if you want. What's h prime of 1? Put a 1 in for x. That's 1 over ln 10. You see what I'm saying? Okay? Put a 10 in for x. That's 1/10 times 1 over ln 10, which would just be that, right? And then put a 100 in for x. That'd be 1 over 100 times ln. That's it. Okay, so don't make it harder than it is. It's just follow the rule, and then you want to plug those in. Now, some of these, all they're going to say is find an expression for f prime. Find a formula for f prime. So you just stop right here, right? H prime, you just stop right there, and that's it. Right? But then here they want you to go ahead and plug those in. All right, let's jump ahead to section 2.7. So that gets you started there. Now let's jump ahead to the next page, on page 147, and let's talk about number 10. Actually, 10 through 13 is all one section. It says g of x is equal to x plus sine x on the interval -5 to 5 This is number 10 on page 147. So it's this first section right here on section 2.7. Okay, so section 2.6 is exponential and log problems, and section 2.7 is trig problems. Okay? Now, notice what it says. I'm just going to read ahead on 10, 11, 12, 13. Does G have any stationary points? Does G have any inflection points? Does G have any local max? Does G have any local min, right? These are chart problems, right? Number line kinds of problems. Number line problems. Okay? So the first one says, does it have any stationary points? Well, how do you find stationary points? Shout it out all at once. What's a stationary point? Where the derivative equals 0, right? So we need the derivative, right? Yeah, which is how our number line problems start. Stationary point. So G prime. Oh, okay, because we got these new rules of how to do G prime. Actually, we didn't need the new rules for this one. Derivative of x is 1. Derivative of sine, cosine. And we want to know where that equals 0. This would be no calculator, by the way. So it's time to know your trig stuff, right? Not on this quiz Wednesday, but the next one. So we're going to subtract 1 from both sides. Where does cosine equal -1? Pi. But we got to be careful now because of that. -5 to 5. So I would agree with pi. If we go around again, that'd be 3 pi. Well, that's like 9 something, so that'd be out of that interval. What about negatives? If you go this way on the unit circle, that's pi. What if you go this way? Negative pi. So negative pi is also a possibility. Now, another way we can do that is not think of the unit circle, but think of the cosine curve. Where does the cosine curve equal -1? Well, down here at pi, but also over here at negative pi, right? So, both of them. Now, a lot of times with the trig one, you get 0 to 2 pi, but not the case here. So there's your stationary points. Now, it wants to know about local max and local min. Well, this is where your number line comes in. G prime. Put those on a number line. I'm going to let you do the rest. Okay? Put those on the number line. Pick points in between. I would pick pi kind of points. Now, 0 is a good one to put in between here. But over here, I'd pick some, pi kind of points instead of 4. Think about it. You gotta pick numbers that you can plug into your derivative. Here's your derivative right here. 1 plus cosine, right? There's your derivative right there. So you don't want to plug a 4 into there without a calculator. You want to plug a pi kind of number so you can get what it is. Okay? All right. So I'll let you finish that. So 10 through 13 is kind of about that kind of stuff. All right. We'll review more tomorrow and tackle some intruders.
I'm gonna be gone Wednesday through Friday.
Ah, shoot.
Yeah.
Okay, so.
So when would be the best time for me to take?
Let me see. Here's what I'd like. Because I'm not sure the review. You would rather take it before you leave, I'm guessing. Wouldn't you?
Yeah.
I mean, here's what I'm thinking. If I could get permission for you to go in to the math office, do it
Yeah.
during the lockdown and everything. I mean, teachers in there, and you can just do it. I think that would be the plan.
Okay.
Let's assume that's going to be what we're going to do. So be ready to
How
go.
long is it?
Well, it's the whole.
Is it after school?
Well, after school it would work, but I've got basketball practice,
Oh.
and so teachers may not be around at all. Then you'd have to come do it in the gym, you know what I mean? I mean, because it's gonna
Okay.
it's gonna
Because
take you
if
time.
not, I do have third block off, but I can't do tomorrow, so which would have worked out nicely.
Oh yeah, that would have worked out really
So
nice.
like maybe Monday third block.
If we can.
Yeah, if we
But you're
can,
good
yes.
with trying
Yeah,
to
I'm
do that
okay
if we
with
can.
that.
Okay.
Alex is at the